Hi, welcome to our module on how machines keep secrets. We'll start with a short module called Encryption 101 that will introduce us to cryptography and give us some definitions of terms to get started with. So encryption is the act of transforming a message so that only someone who has a key can read it. Now the key is any piece of information that's used to guide the encryption. We might, for example, encrypt a message by shifting each letter 5 places down the alphabet in the style of one of those decoder rings we used to get in cereal boxes. So if I had the message, "I want coffee," I might start by collapsing it so that there are no spaces, and then I move each letter 5 letters down. So I becomes N and W becomes B because we wrap around, right? W, X, Y, Z, A, B, and so on. The key in this case is 5, right? Sometimes we would refer to this instead of 5 as its letter equivalent. We say the key is F. Okay. Now, key can come in many forms. Generically, it's whatever information you have to read the message. So let's look at some terminology. We just defined encryption and we talked about a key. Decryption is the act of converting the encrypted message back to the original. That original message we refer to as plain text and the encoded message as the ciphertext. And cipher, the cipher itself, is the algorithm that is used to do the encryption and decryption. The cipher we just talked about is called a Caesar cipher or a shift cipher. The algorithm says each letter gets replaced by a letter, fixed number of spaces down the alphabet. How many spaces down the alphabet we shift is the key. If the shift were 1 character, this sentence would be rendered. Now the key in this case would be 1. A shift cipher is actually not very hard to break. You can break it using letter frequencies, digraph frequencies, the frequency with which combinations of 2 letters appear in a given language, and so on. If the shift cipher is not so sophisticated, one might say, is there any way to improve it? And it turns out that you can make a quite sophisticated cipher that's based on this. And the way that you do that is if you have a different key, a different shift, for every letter in the plain text. Then the statistical approach to cracking the code is not quite so straightforward. So in this variation, the sequence of shifts becomes the key. So in other words, imagine that I decide that I'm going to shift the first letter by 1 character, and the next by 2 characters, and the next one by 3 characters, and then I'll keep repeating that. Right? So my key would be 1, 2, 3, or sometimes we might say it's ABC. The first, second, and third letter, and have that stand for a shift of 1, a shift of 2, a shift of 3, followed by a shift of 1, shift of 2, shift of 3. So if I had the message, Mary had a little lamb, again, I would collapse the spaces out, and then it might be encoded like this. A common way to implement this sort of encryption is to have a longer but easy to remember phrase. So we might have a key such as, "Had we whirled enough in time," right? And then we would translate each letter by a different shift, right? So in this case, "Had we whirled enough in time," H is 8, A is 1, right? D is 4, and so on. So I would shift 8, 1, 4, 23, 5, 23, and so on. And then I would kind of repeat that. So the message above now would be encoded like this. Now, if the key is longer than the message, this turns out to be quite hard to decrypt. But there's still some techniques we could use because the key itself is something that's embedded in real language, and so it has some statistical properties. For doing this kind of encryption, we can make ourselves a tool that'll make it easy to quickly read between our key and the plain text and the ciphertext. It might look something like this. We've seen that a long but finite key is better than a short key. But is there something still better than that? And it turns out, yes, there is. A very long random key is pretty much the gold standard. Suppose I have an algorithm that will produce a sequence of random numbers, and I use it to produce a table like this. Okay. Now what I do is I take a simple message such as this. So this is the secret message that I want to encrypt. And I'm going to render it all lowercase and throw the space and punctuation out and punctuation marks out. And then I'm going to use a simple Caesar cipher, but I'm using the table above. So the first character is shifted by 3, the next one by 9, the next one by 14, the next one by 8, and so on. And eventually it yields this ciphertext. This technique is known as a one-time pad, right? And it turns out it's very effective. If the numbers in the table are truly random, and if the pad is used only once, it can't be cracked if the following criteria are met. The key has to be truly random. The numbers have to be really random. The key has to be at least as long as the message, as the plain text. The key has to never be reused, and the key has to be kept completely secret. So here's a picture from Wikipedia of a one-time pad that's used by a real-world spy agency. Now, as we said above, this cipher requires that the sender and the receiver know which one-time pad was used. Right? So this only works if I know that you were out in the field and you used page 17 of pad 9. Now you destroy yours after you use it, but somewhere in a safe I have a copy of that key. So the thing about this cipher is it requires that the sender and the receiver know which one-time pad was used. Okay? This makes this an example of what we call a symmetric cipher, meaning that the same key is used for encryption as is used for decryption. And so in a symmetric cipher, the security is based on the idea of a shared secret. Both parties know the key. Symmetric encryption can, as we've just seen, it can put a secret behind a very secure lock. The lock can't be picked, but it just kind of kicks the security problem down the road a bit, because now what I have to do is engage in extreme measures to protect the secrecy of the key while also being able to transport it or communicate it to whomever I wish to be able to decrypt the message. So what we'll see next is that there is an alternative called an asymmetric cipher, which can eliminate some pieces of that problem.